Okay, so in the first video, we talked about how to determine valence electrons and why valence electrons were important. We're now going to go through examples of how to draw covalent compounds using Lewis dot structures and valence electrons. So we'll start by trying to draw the structure for CCl4, or as you learned in chapter 3, carbon tetrachloride. So, if we want to draw the picture for carbon tetrachloride, there are a couple rules that we have to follow that'll make this whole thing easier. The first thing that you have to do is count all valence electrons in the bonding atoms. So that means that I have to come over here and look at who's bonding together and how many of them there are, and I need to come up with a total electron count. So for carbon, right, I have one carbon, and every carbon brings with them 4 electrons for all the reasons that we talked about in the last video, right? He's got 4 valence electrons. So that carbon's bringing a total of 4 electrons. Chlorine, there are 4 of them, and each chlorine is bringing 7 because he's in group 7. So he's bringing his S's and his P's, and so he brings 4 times 7 is 28, and 4 and 7 is 28, and 4, 32. Okay, so we have 32 total electrons. So that's me completing step 1. I have to know how many electrons are going to be present for me when I'm trying to draw this molecule, because I need to know who's going to share and how many are they going to have. So carbon brought 4 and each chlorine brought 7, but as I go on and draw the picture, I'm going to assume that these 32 electrons were stripped away from them, and I'm going to hand them back exactly how I want. So I'm going to imagine them being what I call a skeletal structure in a minute. I'm not going to give them these electrons right away. He doesn't have 4 anymore. These guys don't have 7. I've stripped them all away, and they're sitting over here in a big pot, and I'm going to hand them out. Okay, so step 2 says, place the least electronegative element in the middle, and we'll call that guy the central atom. So we went over electronegativity as a trend in chapter 8, but we also know that on our periodic table, we have the electronegativity value written down, right? So like fluorine is written as like a 4.0, francium over here is written as like a 0.7. So look on your periodic table underneath each element, and you'll see the electronegativity written down. As a general hint, it's usually the atom that has a 1 as the subscript. So we'll see here that chlorine has a 4 and carbon has an imaginary 1, and so carbon will go in the middle both because it is the least electronegative, but also he's the one that has a 1 subscript. So typically that rule works if you want to kind of hurry through these problems or not look at the electronegativity. But since they're given, it's not that big of a deal. We're going to then connect the other atoms to the central atom like spokes on a wheel, right? So if I were to do that over here, this is what's known as the skeletal structure step. So we're going to draw the skeleton right now. And that means we're not going to put any electrons, any dots on this Lewis dot structure. So I'm going to put carbon in the middle. I'm going to attach 4 chlorine. So who you put in the middle and how you attach things is incredibly important. So I've just followed step 2. I placed the chlorine around the central atom like spokes on a wheel. And now it says that I need to update the valence electron count to reflect the electrons we used. So when chlorine and carbon bump into each other, they each have to share. I mean, that's what sharing is, right? So carbon has to share an electron and chlorine has to share an electron. If they're each sharing an electron, then that means that that little dash that we just drew represents 2 electrons, right? So in general, single bonds, which we've just drawn, so these single bonds look like these dashes, right? Just whenever I draw one dash like that, I'm implying that we've used 2 electrons, and they're zooming back and forth between the nuclei of carbon and chlorine. So these electrons are residing between these 2 nuclei, zooming back and forth, and there are 2 of them because each nuclei has to share an electron. So if that's true, we just placed 8 electrons, right? Because it was 4 bonds that we just made, and it's 4 bonds times 2 electrons because there are 2 electrons moving back and forth. So that gives me 24 electrons left, right? So that was me updating the valence electron count. So I just executed everything in step 2. The next step, step 3, says place pairs of electrons around the terminal atoms until each one is happy. Be sure to count the electrons as you go to make sure you don't run out, and then place the electrons on the central atom if you need to. Now, happy is obviously a vague term. Happy usually means 8 electrons. Most covalent compounds are sharing electrons because they want to feel like the noble gases. Noble gases all have 8 electrons in their outermost shell. We call that an octet, right? And so most covalent bonds are formed to try to achieve this octet because that's a very energetically stable electron configuration. So typically everybody, all these atoms are aiming for an octet, and that's when they'll be happy. Hydrogen is an exception that we'll talk about right away. There are other exceptions we'll talk about later, but this exception for hydrogen is asking for a duet, which means it can only hold 2 electrons. Okay, so we're going to now hand out pairs of electrons. So when we draw electron pairs, we're going to make 2 dots. We never hand out lone electrons. That's called a radical, and they're incredibly unstable. So we always hand out 2 electrons at the same time. Now I say to start with the terminal atoms first. So central, right, is in the middle. Terminal are the ones that are hanging off of the central atom. So if this chlorine in this picture currently feels like he has 2 electrons, right, then I need to give him 6 more. That is a happy chlorine. Right? He's happy because he has 8 electrons. 2 of them are shared and 6 of them are his own. So I just use 6 electrons to make that chlorine happy. I will also have to use 6 to make the remaining chlorines happy. They're all in the same boat, right? So they all get 6, and now they're all happy. And if I go and check, because then it says place electrons on the central atom if you need to, I go and I check carbon, and carbon feels like he has 2, right? He's got 2 electrons right there, 4, 6, and 8. So he already has 8 around him, but he's sharing all of his. So he's got 8 electrons. So I just gave out 6 electrons 4 times. So that was 24 electrons. And now we have no electrons. When you're placing pairs of electrons, you must use all electrons in your valence electron count. So you must use all electrons available. And that's what we just did, so we're cool. I can't stop if I have 2 left. And I can't give out more than I have. So I said, make sure you count as you go. You don't want to run out of electrons. If I have 24 to hand out, I have to stop at 24. I can't hand out 28 or 30. So you have to make sure that you use exactly the number of electrons that you had in the beginning. So we had 32. We used 32. And I've made a picture of a happy, right? A happy carbon tetrachloride. So those are the 3 steps that we're going to follow again and again to draw these Lewis dot structures. So let's do another practice problem. Oh, there's the picture, by the way, of CCl4. So we drew it like this over here, right? And it's all on one plane, so it looks like these guys are 90 degrees from one another. We're going to start talking on Tuesday about Chapter 10. And we can see that these are all positioned around a sphere in 3D. So these guys actually have really crazy bond angles, and we're going to talk about how we can know what those bond angles are. But this is a model of carbon tetrachloride. Okay, so now we're going to follow the steps again, and we're going to draw a picture for NF3, or nitrogen trifluoride. So again, the first thing that we have to do is count all of our valence electrons in our bonding atoms. So nitrogen has 5 electrons, so he's 5 and he's only 1, right? And then I've got 3 fluorine, and he's in the 7th group, so he's 3 times 7. So that gives me a total of 26 electrons, and I have to use exactly 26 electrons to make this picture. Okay, so there's step 1 done. Step 2, I'm going to place the least electronegative in the middle, or again, it's the one that has the 1 subscript. So if I look over here, the nitrogen has the little invisible 1, so the nitrogen will go in the middle of my structure. I'm going to use these single bonds to attach my fluorines. Right? For now, it doesn't matter how we show them. We'll learn about that early next week. So I had 26 electrons, and I just used 6 electrons to make these single bonds, 2, 4, 6. So I take away the 6 for my bonds, so I keep an updated account. I have 20 electrons left to place, right? So now I can place the pairs of electrons around my terminal atoms to make them happy. So he's not hydrogen, so I don't need to worry about my exception. I just need to make this fluorine feel like he has 8 electrons. So he has 2 that he's sharing with nitrogen, 4, 6, 8. So this guy has 2 already, 4, 6, 8. This guy has 2 that he's sharing, and then he has 4, 6, and 8. So I just handed out 6 times 3. All right, so I just handed out 18 electrons. I have 2 electrons left, and now I have to go back and make sure that I place electrons on the central atom if I need to. This nitrogen right now feels like it has 6 electrons around it. He's sharing 2 with each of his fluorine, so that's a total of 6, but he also wants an octet, and so I can put a lone pair of electrons on my central atom. That will leave me with a 0 balance for electrons, so that's good. I used all 26 electrons, and everybody is happy because everybody here is following the octet rule. Okay, so if I look at this picture in 3D, I can see that this guy's bent down and there's nothing happening up here on top. A little bit like this picture, right? So if I look at this image, these lone pairs that are up here actually occupy quite a bit of space, which is why this guy has this bent down structure, right? So this up here is really these unshared electrons just hanging out up there. So these guys actually push the fluorines down, and we'll talk about that Tuesday during class. But if you read ahead to chapter 10, you'll read about this repulsion theory. But there's the picture of NF3. That's how I would draw his Lewis dot structure. Okay, one more example. So again, I start by counting my valence, right? Hydrogens are in the first group, so that's 2 hydrogen times 1 electron each, right? Plus 1 sulfur, and sulfur has 6 electrons. So 2 and 6 gives me 8 electrons that I have to use to draw this picture. Now, following the electronegativity rule, right, hydrogen has a lower electronegativity than sulfur, I think, although I don't have a periodic table in front of me, so I'm not sure. But as a general rule, hydrogen can never go in the middle. He cannot be a central atom. Because he can only hold 2 electrons, right? Hydrogen is really little and only has access to his energy shell n equals 1. We can recall that when n equals 1, we only have an s subshell, and the s subshell can only hold 2 electrons. So you want to put an atom in the middle that can hold on to lots of electrons, because being the central atom we've seen, you have lots of bonds, right? You're keeping track of lots of electrons. Hydrogen can only ever have 1 bond, right? Because that's how we hold on to 2 electrons, and so he can't go into the middle. He can only ever have 1 bond, so he's never going to be our central atom. So that means by default we put sulfur in the middle. You can see, though, he's following our little hint. He has a subscript of 1, so that right away could have told us that he was likely to go in the middle. So we can put sulfur in the middle. We know we have 8 electrons. I can put a hydrogen here. I can put a hydrogen here. I just used up 4 electrons for those bonds, right? 2 electrons in each bond. So now I have 4 electrons left over to use. My hydrogen, when my hydrogen looks just like this, a hydrogen and a single bond, that is a happy hydrogen. He has 2 electrons, and 2 electrons is what we call a duet, and that's all he can ever have. So that's what every hydrogen you ever place will look like. That means the sulfur has 2 4 electrons, but he wants 8, right? Sulfur wants us to have, he's trying to get an octet. So in order to have an octet, we have to place 2 electrons here and 2 electrons here. That's us using our 4 electrons, and that's us making a full, happy dihydrogen sulfide, dihydrogen monosulfide. So there's that picture. Now, we said before in that last example that these lone pairs actually take up a lot of space, right? They kind of occupy a big orbital, and they fly all around, and they repel other things. So if we look at a picture, this is a computer model of H2S, we can see that these lone pairs here, right, are occupying a ton of space and pushing these hydrogens out of the way. It's kind of like a weird Minnie Mouse. There you go. So they're pushing the hydrogens out of the way. Again, we'll talk about that when we get into Chapter 10. But there's a picture of H2S using the duet rule for hydrogen and the octet rule for sulfur. Okay, last example. Now we're going to look at ions, right? Ions. Everything we've done so far has had a neutral charge, but this is nitrate, a polyatomic ion that you had to memorize in Chapter 3. It carries a -1 charge, the 1 is implied. So when we're adding up the valence electrons in the bonding atoms, we just have to watch out for charges. Anions have a negative charge, and that means that they've picked up along the way extra electrons. You're going to add extra electrons. So this guy just has 1 extra electron. So we're just going to add up all of our valence, and then we'll add up that extra. We'll add that into the pot of electrons. If this were a cation, which we have a few we could draw, that means that they're positive. Oh boy. If they're positive, that means that they lost an electron. Right? They lost electrons, and so we're going to subtract their charge from the electron count. Subtract charge. We can go over one of those on Tuesday when we all come back to class. I'll give you an example of this. But here, because it's an anion, we're going to add that extra electron. So when we add the valence, it'll look like this. Nitrogen, of course. Oh boy. There's 1 nitrogen. He's bringing 5 electrons. We have 3 oxygen. He's bringing 6 electrons. He's in group 6. So we have 5 plus 18 gives us 23. As a side note, remember we said we always hand out pairs of electrons. Always pairs. So we are always going to need an even number here. If we don't have an even number, that's when we know something weird's going on. Because if I have to hand out pairs of electrons, I need this to be an even count. So we're going to come down here and we're going to add on that extra electron. He just comes down here and jumps into the count. And so we will have 24 electrons to hand out. That's really the only thing that we have to do differently when we draw these ions. All the other steps follow in the same way. But we have to watch out for adding or subtracting away the charge. Okay, so now step 2 says place the least electronegative atom in the middle, so that'd be nitrogen. I'm going to attach the oxygens around the central atom. So we just used 2, 4, 6 electrons, so I'm going to update my count. Those went into my bonds. I now have 18 electrons left, right? So I'm going to hand them out in pairs. I'm going to go to the terminal atoms first, right? That's what I've been doing this whole time, but just a reminder. So I'm going to go to this oxygen. He has 2 electrons that he's sharing, so he wants 6 more. All the oxygens are in the same boat, so they all get 6. I just handed out 18 electrons, and I'm all done. But there's something wrong, right? I'm all out of electrons, and nitrogen only feels in this configuration as though he has 6 electrons. So he has 2, 4, 6. That's not a stable or correct Lewis dot structure. Nitrogen's only going to stay here and hold this molecule together if he has 8 electrons. So he's hanging out with 3 oxygens that have hoarded all the electrons on their nuclei, right? All these oxygens are feeling pretty happy because they have all the electrons that they want, but one of them is going to have to share more. So when we run out, right, I said we place the electrons on the central atom unless we've run out. So here we are, we've run out. Now we have to bring in step 4. Step 4 says if you run out of electrons, then an electron-rich element or atom must share with the electron poor. It's like Robin Hood, right? Or Bernie Sanders. Okay, I'm done. So, no more political talk. So, the electron-rich, any one of these oxygens could give 2 electrons, not just give them to nitrogen, but share them with nitrogen. So let's say we take these 2 away, right? We make those 2 go away. They're not his anymore. Instead, he throws them here in the middle, and we make a double bond. So step 4 is where we might, if we need to, add a double or triple bond. We didn't need a triple bond this time because now nitrogen's happy, right? This oxygen's happy. This oxygen in this configuration has 2 pairs of his own electrons, right? And then he's got 2 pairs of shared electrons. But all told, that makes him feel as though he has 8. This nitrogen feels like he's got 8, but he's sharing all 4 pairs. And then these last 2 oxygens feel happy because they each have, right, they have 1 shared pair. And then they have 3 lone pairs that they're not sharing. So as long as every element meets this octet rule, except hydrogen, as long as the elements meet the octet rule, it doesn't matter how they do it, through sharing or through electron pairs. But we had to invoke step 4 here because the central atom wasn't happy and we had run out of electrons. So we had to give these away. I don't really know how to make an eraser come up, but we'll imagine. Oh, wait. No, that's not an eraser. Okay. Oh, no. No. Okay, so no eraser, but, oh, now he's a pointer. Okay, well, anyway, so those had to go away. He chipped them in, he shared them better, and now everybody's happy. So this is what this picture would look like. It actually exists in a plane, and here we can see the double bond, right? This shows us where this oxygen is actually sharing 4 electrons. Okay, so those were examples of how to draw Lewis dot structures based on valence electrons and sharing patterns. So you guys need to practice some of those. I'll post a worksheet that we used in class. I'll post that on Blackboard under Chapter 9, and you guys can keep practicing this. You can email me at any time over the weekend if you have questions. I have tutoring on Monday, 1:30 to 3:30, or you can email me if you need to meet with me. But you need to make sure that by Tuesday evening when you come to class, you have a pretty good idea of how to draw these Lewis dot structures because we're going to hit the ground running. Okay? Enjoy the rest of your break.